After last class, hopefully we all feel confident with the particles of the atom, the protons and neutrons and electrons, and how they come together to create your mass, and also the difference between your mass number and the average atomic mass. Now that we've got a good understanding of that, we're going to move into ions and isotopes, so changing around some of those particles. So first, let's take a look at isotopes. What do we know is the one thing that never changes, or we change the atom? Protons. Protons never change, all right? So in isotopes, protons stay the same, all right? But these atoms have different number of neutrons. Isotopes change the number of neutrons. Well, we know that protons plus neutrons equals mass. So that means if I change my neutrons, I have now changed my mass. So for example, down here I have carbon 12 and carbon 14. This 12 and 14 tells me the mass number of that carbon. So I know that the mass is changed, therefore these two carbons have a different number of neutrons. All right, if we look over here to the left as well, we've got some examples with helium. All right, so looking at helium-5 to start out with, I've got 2 protons. As usual, if you look at your helium on your periodic table, you should see that it has 2 protons. All right, and then I have 3 neutrons that add together to give us our mass. So helium-5, 2 plus 3 is 5. Helium-6, still only our 2 protons. Remember, that never changes. But now I have 4 neutrons. 2 plus 4 equals 6. So that's where I get my helium-6 from. And then helium-7, again, I have my 2 protons as usual. My 2 little red dots. All right, and then I have 5 neutrons this time. That gives me a mass of helium-7. Lastly, one more example here is 2 protons. Remember, notice that never changed. If that would have changed, I would have no longer had helium. And this time, I have 6 neutrons. So that gives me helium-8, 2 plus 6. So your number of neutrons changes your mass. Because these are all different atoms of helium, we call them isotopes because they are all helium, but they're basically different versions of helium, different masses of helium. All right, so same protons, different neutrons, isotopes. So let's look at how we would notate this. This is isotope notation, also known as hyphen notation. All right, so you may see it referred to as both. Starting out here with our chemical symbol so that we know what chemical or an element we're talking about, with a hyphen, hence the name hyphen notation, and then the mass number. All right, so remember mass is protons plus neutrons. So this number is just letting us know which specific helium we're dealing with. So now let's take a look at some examples that are in your packet, and let's do these together. So we've got 2 different isotopes of aluminum and 2 different isotopes of copper here. All right, so our chemical symbol, what do you see as the abbreviation on your periodic table? For aluminum, we have Al. All right, number of protons. We know that number of protons never, ever, ever changes. That's your atomic number. All right, so our atomic number of aluminum is 13. All right, protons equal electrons because it is neutral, so that is also going to be 13. And now I want to find my neutrons. Well, how do I find neutrons? I'm given mass. What does this number 27 tell me? That tells me the mass. So now I can do mass minus protons equals neutrons. So 27 minus 13 gives me 14 neutrons. All right, aluminum 28. Again, I still have the same chemical symbol. I didn't change what element I'm talking about. Aluminum. Number of protons, or my atomic number, did not change, right? Remember, that never changes, or I would have changed elements. So that's, again, 13. Dealing with neutral elements, so protons, number of positivity, and the amount of negativity has to be equal. And so now we can find our neutrons. Mass, 28, minus 13, gives me a number of 15 neutrons for aluminum 28. So notice here's 2 examples of isotopes. Same exact element, both aluminum. Everything is the same except my number of neutrons. Neutrons changed, and therefore that changed my mass. All right, and so that mass number lets me know what specific atom of aluminum I'm dealing with. All right, so looking at another example here, we're looking at copper. Copper, make sure you read your periodic table closely. is abbreviated with Cu. All right, it's not Co because Co is already taken by cobalt. So copper is abbreviated with Cu. So find Cu and find your atomic number, which would be 29. All right, knowing that our protons and electrons are equal, I've also got 29 electrons because I have a neutral atom. All right, so in order to find my neutrons, I'm going to do mass, which is 64 minus 29. And that's going to give me a number of neutrons of 35. All right. Same thing. I got another isotope of copper because they're both copper but with different masses. So abbreviation is the same. Atomic number and number of protons is the same. And it is still neutral. So I still have only 29 electrons. So now I'm going to do 60 minus 29. I'm going to get 31 as my number of neutrons. 60 minus 29, new mass minus protons. So notice everything is the same, but what gave them a different mass was their number of neutrons changing. So that's what you need to know about isotopes and how your mass changes according to your neutrons. And so now we're going to take a look and switch gears into ions. As an introduction to ions, we're going to take a pause and we are going to do this activity together as a class. Taking a look at ions now. Ions are atoms with a positive or negative charge. All right, so we know that our positive comes from our protons. All right, protons are positive, and the negative charge in our atoms come from our electrons. And so for them to have a positive or negative charge, that means these two are no longer present in equal amounts, all right? We have more protons or more electrons than the other. So there's an imbalance here. We know that our protons can never change, all right? So protons never change. So in order to give our atom charge, what has to change? Electrons in ions. Electrons change and therefore result in a charge to your atom. So when we look at ions, they are atoms with extra or fewer electrons compared to their neutral atom. Depending on whether or not you have extra or fewer electrons leads you to either a negative ion or a positive ion. So let's take a look first at negative ions. We call these anions, all right? Those are the names for negative ions. So if I said that protons can never change, all right, what does that mean about my electrons in order to make something negative? If I have, for instance, 3 protons and 3 electrons, right now it's neutral. But if I wanted to make this negative, what would I need to do? I cannot change my protons. Those cannot change. So what would I need to do in order to make it negative? I would need to add another electron. And now look, all of them cancel out except for that last electron. So then this will be negative by 1 electron. So negative ions have more electrons. More electrons. Then when we look at cations. Cations are our positive ions. One way to remember this, if we look here, this T in cation looks like a plus sign. All right, so cations are positive. Does this mean that they have more or less electrons? So in order to be positive, I've got, let's say again, 3 protons and 3 electrons. Again, I cannot change my protons. So what do I need to do to the electrons in order to make my ion positive? I would need to get rid of one, right? So some atoms lose electrons. So if I look at this now, everything cancels out except for this one positive proton. So then I would have a positive 1 charge. That means when I'm looking at cations, they have less electrons compared to their neutral atom. All right, so cations lost negativity, anions gained negativity. So let's take a look at ions here, all right? So when we're talking about ions, all right, we are changing the number of electrons, Therefore, we're talking about gaining and losing negativity. All right, because electrons are what? Negative. So we're gaining and losing negativity. So think about it in comparison to your life. Imagine the little atoms all have a life, right? And all the protons are the positive people in their life, and all the electrons are the negative people in their life, right? So I never want to change the number of positive people, right? We want to keep all of those. We never want to change it. We never want to let go of it. So our positive people, or our protons, stay the same. Always protons equal the same. Never want to adjust the positive people. What may happen is we're going to gain and lose the negative people in our life, right? Negative people come and go. So if I gain negativity, or I gained negative people in my life, gain negativity, I am now negative, right? So gaining negativity or gaining electrons, because that's where that negativity comes from. On the other hand, if our atom loses negativity, all right, so it gets rid of some of the negative people in their life, it now becomes positive. All right, it got rid of the negativity. All right, so think about it as gaining or losing negativity in your life. If you gain some negativity or you gain some electrons, you're now a negative person. If you lose the negativity in your life, you lost the electrons, you're now a positive person. All right, so that's one way to help you think about how the charge is impacted by gaining and losing negativity. So let's look at some examples here. So you have these practice ones in the bottom of your notes. Let's look at chlorine. So what we call the chlorine ion is chloride, and we'll get into that a little bit more in your naming unit. But let's take a look at chlorine. So the atomic number of chlorine is 17. All right, remember, we always know the atomic number. That atomic number matches the number of protons that I have. All right, so if you'll notice, this one already gave us our mass and our neutrons. Yay. So double checking it, 17 plus 18 gives me 35, which is the mass they gave us. Already found that. We didn't have to find anything. Great. All right, so but what we're looking at here is electrons. So I need to go see if my chlorine has a charge, which it does. It's just a minus sign. So when you see just a minus or just a plus by itself, there's an assumed 1, just like in math class where you have X and it's assumed there's a 1 in front of it. All right, so this chlorine has a -1 charge. So what does that mean? Does it have more or less electrons? Did this chlorine gain negativity or lose negativity? It gained negativity. How much? It gained 1 electron. So when we look at it, we used to have 17 electrons when it was neutral, but we just said it gained an electron. So now it has 18 electrons. All right, so if we look at that, and I say I'm going to write 17 protons, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, all right? And when it was neutral, for every proton, I had an electron. All right, and so each of those were able to cancel out, all right? There was 1 electron for every proton that was present, all right? So think about it as your bank account. You added 1, took 1 out, added 1, took 1 out, and we were at 0. But then, now I have 1 more electron. All right, so I'm going to add it up to the top because I don't have any room at the bottom. But now I added another electron. There's no proton to cancel that out anymore. So now I'm negative by how much? I'm negative by 1. So I have a -1 charge. That's what you're seeing here. When you add an electron, now I have 1 more electron and no proton to cancel it out. So I end up with a -1 charge on chlorine. So essentially, you're doing the opposite. If it's -1, then you're adding an electron because we're dealing with negatives. All right, so let's look here. Another example. Oxygen, 2-. We call this oxide. Atomic number is 8. You'll see that on your periodic table up top. And then it gives us the mass, which is 16. So we know our atomic number and our number of protons are the same. So 8 and 8. Neutrons. This time we need to find our neutrons. So neutrons is mass minus protons. All right, so our mass is 16, our protons are 8, so I have 8 neutrons. Now, for what we're talking about with our ions, we're looking at our number of electrons. Well, oxygen originally had the same as its number of protons, right? But look, big key up here, I have a -2 charge. So that means, did I gain negativity or did I lose negativity? I gained it, right? I gained 2 additional negative particles. So instead of 8 electrons, I now have, I wrote 10 instead of writing 8 plus 2 equals a total of 10 electrons. All right, so I gained 2 electrons. So then I now have 10. So if we look at it, I'd have 1, 2, 3, 4, 5, 6, 7, 8. And then for every proton, you had an electron. But then I gained 2 more, right? So for each of these, I canceled out. They canceled out to 0 and everything was neutral. But then I get down here and look, I have -2. So that's where you get that charge from. And last example we're going to look at here, strontium. Strontium 2+. All right? Atomic number for SR would be 38. Remember, it's the same as your number of protons. It's also on your periodic table. And then we have a mass of 76. All right, so we need to find our number of neutrons. Well, neutrons is mass minus protons. So 76 minus 38 equals 38 neutrons. All right, and then we're taking a look at electrons. So I look up here and I see that I have a +2 charge. Well, in order to be positive, did you gain or lose negativity? You would have had to lose the negativity in your life, right? So how much negativity did I lose? I lost 2 electrons. I lost 2 people of negativity. All right, so when I originally had 38 electrons, when it was neutral, I've now lost minus 2 of them. All right, so I only have 36 electrons. So if I look at it and I have 38 positives and 36 negatives, what do I have more of? I have more protons, so that's what made it positive by 2. So let's take a look at this nice Venn diagram that kind of compares everything that we've been talking about between the neutral atom and their ion and isotope of each. So let's start with what is the same in all 3 of them. All 3 of them have the same atomic number, which means the same number of protons, right? Because that's what our atomic number tells us. And therefore, they are the same element because that element is identified by its protons and its atomic number. All right, so that's what never changes. But then when we're looking at our ions, ions change the different number of electrons. So we gain or lose electrons to get a positive or negative charge. If I gain electrons, I'm now negative. If I lost electrons, I'm positive. So ions change electrons. The other version we can have is our isotopes. Isotopes change neutrons. All right, and as a result, because neutrons contribute to mass, all right, therefore they end up with a different mass number. So they contribute to mass and therefore give us a different mass number. So isotopes change neutrons. All right, that is compared to your neutral atom that has no charge and found on the periodic table. All right, something that the neutral atom and isotope have in common is that neither one of them have a charge, right? Protons and electrons are equal between our neutral atom and our isotope. But once we get over here to ions, they change the number of electrons and therefore we end up with a charge, different number of electrons than our protons. All right, so neutral atom, then we have our ions changing electrons and our isotopes changing neutrons. So last part for today is going to be looking at calculating average atomic mass. So we talked about the number on the periodic table. The periodic table gives you for mass is an average. That is an average of every possible version of that element known to man averaged together by its abundance to give you an average mass of what exists. So, because of the existence of isotopes, right? Isotopes change neutrons. Isotopes change the number of neutrons and therefore change mass. We then have a collection of atoms that has an average value, because based on how many neutrons each version of that atom has, the mass can differ. So we're going to calculate that average atomic mass now. In order to do that, you've got 2 steps that you're going to follow. So you've got some bullet points there for steps. Step 1 is going to be to multiply the decimal percent by the mass of each isotope. All right, multiply the decimal percent by the mass of each isotope, and then 2, add all products together. All right, so give you a second to write that down, and then we will look at the examples at the bottom of your page. All right, so example 1 here, we have boron. All right, boron is 20% boron 10 and 80% boron 11. That is, all of boron that exists on Earth, 80% is found to be boron 11. So find the average atomic mass. So in your notes, step 1 tells you to multiply the decimal percent by the mass of each isotope. So let's identify each isotope. I've got 20% of boron 10 and 80% of boron 11. So the decimal percent would be moving that decimal forward twice, and you would have 0.20 times 10, which is the mass. Here's our mass of that isotope, which would give us 2.0. All right? Then the second one, I would have 0.80 times 11, because that's the mass of my second isotope, which equals 8.8. All right? And then step 2 tells us to add those 2 products together. So then I would get 10.8. All right? So let's compare that to what you see on the periodic table. All right, notice we kept our significant figures here, 2 sig figs, 2 sig figs, and then 1 decimal place when I added it together. So let's look at the periodic table. The periodic table in front of you gives you a mass of 10.811 AMUs. All right, so look at the difference. We're right on, right? But they have more decimal places, right? So significant figures are all subject to how you measure and what your percents are given in, right? So in order to put on the periodic table, we have some smart, fancy scientists off in a lab somewhere who can give us very, very, very precise measurements, right? Very precise percentages. So that's where you get those extra decimal places, that somebody has put in the extra work to be able to give you those extra decimal places and a more exact answer. All right, but as you can see, that compares and is the same as what is on your periodic table, just with not as much specificity. All right, let's look at example 2. Example 2 here. An element of copper has naturally occurring isotopes with a mass of 63 and 65. The relative abundance of the atomic masses are 69.2% for a mass of 62.93 and 30.8% for a mass of 64.93. Calculate the average atomic mass of copper. So step 1, multiply the decimal percent. So let's look at our first one. We've got 0.692 times the mass of 62.93. And that would give us 43.5 using our correct sig figs. 3 sig figs present, so our answer can be in 3. All right, so then multiplying the decimal percent of our second isotope, which would be 0.308 times 64.93. And that one would give us 20.0. Once you round it, you get like 19.998, which would round to 20.0 as 3 sig figs. So add together those products, and you get 63.5 AMUs is your average atomic mass for copper. All right, so now we're taking some very specific atoms of copper and we're adding it together to find the average atomic mass based on your percent abundance. All right, and then last example here, calculating average atomic mass of sulfur. If 95% of all sulfur has a mass of 31.972. Now another 76% has a mass of 32.91. And then lastly, 4.2% have a mass of 33.967. So we see that sulfur here is present in 3 different isotopes. All right, so 95% or 0.9500 is present at 31.972 AMUs. When we multiply those together, we get 30.37. So I took care of that one. The next one is 0.76% have a mass of 32.971. So move that decimal forward twice and we get 0.0076 times 32.971. All right, you multiply those together, keeping our sig figs. I only have 2 in 0.0076, so I get 0.25. All right, and then lastly, I've got 0.0422, so that's your 4.22%, is present at 33.967 AMUs. So we're going to multiply those together, and you'll get 1.43. Add those products together as your second step, and you get 32.05 AMUs. All right, that is the average atomic mass. If I looked at all of the sulfur that existed and in its abundance, that's what I would get for my value.